In our previous two lectures, we talked about a nonlinear component diode, and we analyzed circuits that contain diodes, LTI resistors, and constant sources. Okay? Even though diode was a nonlinear component, it allowed for a piecewise linear analysis. And in this lecture, we will talk about another such component, a nonlinear component, but it yields to piecewise linear analysis. But there's a main difference between the diode and the component that we will talk about today, namely the operational amplifier. And that difference is that diode was a passive component, whereas operational amplifier is an active one. Okay. So, and it's a little bit more sophisticated than a diode. By an operational amplifier, we mean the following. It's a device with many terminals, 6 or sometimes more terminal device. Okay. And usually it's drawn like this big triangle. Okay. The tip of the triangle is where the output terminals, output terminal sticks out. And then we have the terminals here. Okay. Usually for analysis, those 3 terminals are, or those 3 nodes are the nodes that are essential. Okay. Yeah. Plus, minus. There are some other terminals too. Ground. E plus, E minus, and this terminal is called non-inverting. Input terminal. This is called inverting input terminal. Okay, and this is our output terminal. Okay. Now, let me try to explain what those terminals stand for. Now, E plus and E minus, okay, they are connected to DC voltage supplies, DC voltage supplies. Okay. And because of that power input to the device, if we consider all those DC supplies within that device, this device can be considered as an active device, okay, active component. Therefore, it's able to provide supply power to the circuit that it's part of. The values E plus larger than E minus determine, okay, the band, okay, the interval within which the output voltage can reside. Turn the upper and lower limits of the output voltage. The output voltage. Which we denote by V sub O or V sub 0. That is the output voltage always lies within this interval, okay? Lower bounded by E minus and upper bounded by E plus. Now, the transfer characteristics is as follows. And suppose E plus and E minus, those voltages, they have equal magnitudes but opposite sign. So suppose E plus equals something, ES, and E minus equals minus that thing. Okay, minus ES. In general, we don't need such symmetry, okay? But for the sake of simplicity, we're going to take E plus and E minus having the same magnitudes but opposite sign. Okay, 12 volts minus 12 volts, 16 volts minus 16 volts. And how this device works is as follows. It senses the voltage difference between these two terminals, plus and minus, and in the output it generates a voltage that's proportional to the voltage drop from this node to that node, okay, from plus to minus. And then, of course, provided that output voltage falls into this range. If it doesn't, then it's either E plus or ES, which we say the op-amp has reached positive saturation region, or it equals E minus, that is minus ES. In that case, the op-amp is said to have reached the negative saturation region. Okay. So this is V plus minus V minus, let's say the horizontal axis, the origin, and here, vertical axis, the output voltage. And what we have is that in some vicinity, the origin, okay, the output is proportional to the difference V plus minus V minus. Okay. And then after some time, or when the output voltage reaches either the upper bound or the lower bound, then it stays fixed. It can never get beyond the positive saturation voltage or the negative saturation voltage. Okay, this is ES, this is minus ES, and here the slope, suppose that is denoted by some number A. Okay. Now when the output voltage depends linearly or proportionally to the difference V plus minus V minus, we say the op-amp is in linear region. Okay. So this is the linear region. Okay. When the output voltage gets fixed at the positive saturation voltage, we say the op-amp is in positive saturation region. Plus saturation. Okay. And on the other side, on the left side, we have the negative saturation region. Okay. Now, this A, the slope, is called the open loop voltage gain. Okay. A is open loop voltage gain. And in almost all the applications where we use an op-amp, its use, its benefit comes from two important properties. One of them is that this A is very large. So large, in fact, that it would be a nice approximation to take it infinitely. And the other property of the op-amp, which makes it a useful component, is that the inputs, the input currents from the non-inverting and inverting input terminals into the op-amp is very, very tiny. Okay, so tiny, in fact, that for analysis, we will take it to equal to 0. And that will give us a very nice approximation. So typically, A is very large, around 200,000. Okay. Now, Here, let's be precise about the notation. V out, as we said, is the voltage of the node voltage of the output terminal with respect to some ground. Okay. Voltage of the output terminal. V plus is the voltage of the non-inverting input terminal. Okay. And V minus is the other input voltage, the inverting input terminal. Okay. And they're all with respect to some common ground. With respect to some common ground. Now, op-amp, in short, for operational amplifier, has 3 operating modes. The linear mode, positive saturation mode, or the negative saturation mode, or region. Okay. Now, one, it's called the linear mode, where V out equals the difference between V plus and V minus times the gain. Okay. And the output is between negative saturation voltage and positive saturation voltage. We have the positive saturation mode, where V out is fixed at positive saturation voltage, ES, and this product of gain and voltage difference is larger than ES. Okay. And the third mode is the negative saturation mode, where V out is now fixed at the other saturation voltage, okay, plus 16, let's say, and minus 16. And this time, this product is smaller than minus ES, okay, negative saturation voltage. Now, sometimes op-amp can be modeled by the components that we have already introduced, namely LTI resistors and the dependent source. Okay. And that model has the following topology. Dependent source model of an op-amp. Operating in a linear region. So here we have between V plus and the positive node and negative nodes are connected by a very large resistor. Okay, V plus here, V minus here. Here we have the input resistance, and for the output side, we have the output resistance, RO, and that's connected to a dependent source. And the voltage that the dependent voltage source provides is the gain times the voltage drop across the terminals of this input resistor. Okay, that's the detail. Now, Rin is called input resistance, And one nice thing about input resistance is that it's very large. So large, in fact, that we will be able to, for most of our analysis, we'll be able to consider it as an open circuit. And once this is open circuit, it means that input through the input terminals to the op-amp can be taken safely to be zero. This is about 1,000,000 and 1,000 billion ohms. Okay, in that range. Our out is called output resistance. And it's in the range 10 to 100 ohms. And A is the voltage gain. It's in the range 100,000 to 100 million. Okay, volt per watt. It's a unitless parameter. Now, for many applications, it is reasonable to work with idealized models, okay, with the ideal op-amp model. Okay? Because working with the ideal op-amp model instead of more realistic op-amp model, we get something different than the actual answer, let's say, but that difference is so tiny that it's reasonable to work with the ideal op-amp model because the analysis become significantly simpler with idealized models. Okay? There are two idealizations. One of them is called finite gain. Ideal op-amp model. Where input resistance is taken to be infinity, output resistance is taken to be zero. Therefore, we're taking this as open circuit, and here this part as short circuit. But we let A to be finite, very large, finite number. And a further idealization, in a further idealization, we take this gain also infinity, infinite gain. Is where input resistance is infinity, it's open circuit. The output resistance is zero, it's short circuit, and A is infinity. And most of our analysis of circuits with operational amplifier component will use this infinite gain ideal model. So let's therefore talk a little bit about infinite gain ideal model. let me redraw component. Okay. B plus, B minus. Here we have I plus, and here we have I minus. The currents into the op-amp from non-inverting and inverting input terminals. This is our output terminal, V out, and this current, let's call it output current into the op-amp. Okay. Now, infinite gain op-amp is such that because we're taking the input resistance to infinity, these two currents can be taken safely to be zero. Okay. So I plus equals I minus, and it's zero. And that condition or that equation holds true regardless of the region that op-amp is operating in. So this is an all region condition. Okay. The currents from the input terminals is zero. Remark. Zero, not equal to zero. Sometimes, because the only important terminals for our analysis is this V plus, V minus, and V out, okay? Or only voltages important are those three voltages. So we only draw those three terminals, and sometimes people tend to think this as a closed surface and apply KCL. Since these two currents are zero, this is a result of KCL. Must also be zero. But the thing that we have to be careful about is that this is not a closed surface. Okay, there are many terminals. For instance, there is a ground somewhere, let's say, and also some terminals to which we connect the DC supply, since perhaps some other terminals. There are many terminals that we're not drawing. Therefore, this is not a closed surface. So the output terminal, the output current is not zero. Okay, in general. So that's something that you should keep in mind. And we can make the following table. Linear region, positive saturation region, and negative saturation region. Now in linear region, minus, yes, let's look at V out, yes. So the output voltage is in between minus yes and plus yes, between negative and positive saturation voltages. And now, since the output voltage is A times the difference, V plus minus V minus, so V plus minus V minus cannot be anything different than zero according to this model, because something different than zero times infinity gives us infinity, and the output voltage can never be infinity. Okay, so in linear region, according to the infinite gain ideal type model, V plus and V minus, they must be equal to 1, so that the difference is zero, and what we have is infinity times zero, and infinity times zero can be anything you want. Okay, and what we want is we want output voltage to be between minus yes and yes. So in positive region, there's nothing to compute or analyze about the output voltage. It's fixed. Okay. And the question is, when do we hit the positive saturation region? It's when V plus becomes larger than V minus. Okay. And negative saturation region is the opposite. V out this time is fixed at the negative saturation voltage minus yes, and the condition here is reversed. V plus is strictly less than V minus. Okay. So those are the V plus V minus conditions and the constraints on the output voltage depending on the region. Okay, so this is something that's part of the model, and we have this as part of the model. At all regions, I plus and I minus, these two currents are zero, and that's all we need to be able to analyze circuits that has operational amplifiers in them. Okay. So we can draw the following: V out versus V plus, V minus difference curve. Okay, so V out, whenever this difference is positive, that is V plus is larger than V minus, V out is fixed at plus S. Whenever this difference is negative, that is V plus is less than V minus, V out is at minus ES fixed. And when the difference is zero, that is V plus equals V minus, the output can be anywhere on that line segment. Okay. Hence, this part is positive saturation region, this part is negative saturation region, and here this part is linear region. Okay. Now we will see and obtain the input and output characteristics for some useful, widely used operational amplifier circuits. Okay? And in our analysis, we have used the finite gain ideal op-amp model, where the model is this condition together with this table. Let's begin with one of the simplest op-amp circuits, namely the buffer or voltage follower. Okay. So this is the circuit. This is the output voltage, and here we have the input voltage. Again, okay, these are voltages with respect to some common ground, and this is positive, this is minus. And what we have here is we connect the inverting input terminal to the output terminal. Okay, like this. Therefore, V minus and V output by this connection are forced to be equal voltages, and this, where output is fed back to one of the input, is called feedback connection, and because we're connecting it to the minus negative labeled terminal, this is called a negative feedback. Okay. Now what we will do is we will try to figure out the relation between the input voltage here and the output voltage there. And to be able to do that, what we will do, we will use the model that's given in this this condition and that table. Okay. So what we do in analysis with op-amp circuits is the following. The procedure is quite simple. What you do is you write V plus, okay, this voltage in terms of input and output voltages. You write to express V minus in terms of input and output voltages, okay, and then those two expressions will be valid in all regions, okay, because you don't make any assumptions about the region in which the op-amp is in while obtaining those two expressions. And once you have V plus and V minus in terms of input and output voltages, you figure out the input-out relationship through this equality, okay, when the op-amp is in the linear region. So you obtain the relation from input to output voltage when the op-amp is in the linear region. Also, using this constraint on the output voltage, you figure out a constraint on the input voltage so that the relation between input and output is valid. And then you carry your analysis to positive saturation region and negative saturation region. Now, there's nothing to compute as for the output voltage when the op-amp is in positive saturation region. It directly equals Ts, whatever Es is. All you do from the analysis point of view is using this constraint V plus larger than V minus, you find a relation between, or you find a condition on the input voltage so that op-amp is in positive saturation region, and you do the same thing for negative saturation region. Okay. So the procedure is, therefore, is quite straightforward. So let's write down V plus and V minus in terms of input and output voltages. In this particular topology, it's extra easy because V plus is directly V in, so there is nothing to really compute, and V minus directly equals V out. Again, there is nothing to compute. Okay. So V plus equals V in, and V minus, because of this feedback connection, equals V out. Okay. And now we can start with these expressions. We're now ready to start our region by region analysis. Okay. Suppose that the op-amp is in linear region. Now, linear region means that V plus equals V minus. So V plus is here, V minus is here. So in linear region, the output exactly equals the input. Okay. That's why this circuit is called voltage follower. The output follows what the input voltage does. Okay. V plus equals V minus, and minus yes less than or equal to V out. Greater than or equal to minus yes, and smaller than plus yes. So that implies, because V plus is V in and V minus is V out, that implies V out equals V in. And you plug that V out expression in terms of V in to this constraint, and you obtain a constraint on the input voltage. And minus yes less than or equal to V in less than or equal to yes. Okay, so what we did is, first we computed this, and then we replaced this V out with the expression in terms of V in, and that gave us a condition on input voltage. Okay. So what this says is, the output will follow the input voltage, provided that input voltage is small enough, and by small enough, we mean it's between minus yes and plus yes. As for the saturation regions, there's nothing to compute about the output voltage. Output voltage is fixed at ES plus 16 volts, let's say. All we do, from the analysis point of view, for positive saturation region is we try to figure out the condition on the input voltage, so that under which the op-amp is in positive saturation region. So V plus is V in, V minus is V out, V out is ES. Therefore, as long as V in is larger than ES, then the op-amp is forced to enter the positive saturation region. V in larger than ES. And likewise for the negative saturation region. Okay, these are the piece of information coming from the model or from the table, and using that we figure out that V in must be less than minus ES, or whenever V in is less than minus ES, the op-amp is in negative saturation region. Okay. Now let's put all that information into an input-output, or the transfer characteristics curve. V out versus V in. It's the origin. Okay. So what we have figured out is the following for the voltage buffer, for the voltage follower buffer. As long as the input voltage is in between minus ES and plus ES, V out exactly equals V in. Therefore, the slope of that line is 1. V0 over V in is 1. Okay. Then, when V in becomes larger than ES, the output no longer follows Vin, but gets stuck at positive saturation voltage. Okay, so when you increase Vin further to the right for this vertical line ES, the output stops following the input and it remains constant at plus 16 volts, let's say. And similarly happens with negative saturation voltage. When you decrease Vin further from minus ES, what happens is V out no longer follows V in, but it gets stuck at minus 16 volts. Okay. Now, what's the use of such circuitry? The key lies in the fact that the current through this terminal into the op-amp is zero. Okay, that's a very important property of this construction. What we want is, what this does is, it takes this information, voltage information, and it carries to the output node. But while doing that, it doesn't take any current from where this terminal is connected to, where that circuit is connected. Okay. So that's an important use of buffers. Buffers are widely used to isolate two ports, let's say. Okay, here we have 2-port. Let's call it N1. And suppose that this is some circuit which takes some measurement from the physical world and generates or transforms that physical information to electronic information, let's say as a voltage across the terminals of its second port. Okay? Here, let's say voltage equals temperature in some room. And this circuit you design, which transforms the temperature information to voltage information, under the assumption that this pair of terminals is a left open circuit. Okay? Then clearly, when you do that, your design, under the assumption that this pair of terminals is open circuited, when you connect some other device, some other 2-port to this, the whole circuitry changes, because this is no longer open circuit. The circuit that you connect to this starts getting some current from this 2-port, and then when there's some current over that wire, this is no longer open circuit, and your design condition breaks down. Therefore, your design may not be successful at that point. Okay? But this information, voltage information, let's say, which carries temperature information, you want it to be used by some other circuitry. Okay? So that circuitry makes a decision, and according to that decision, you either increase the heat that's being pumped into the room to make the room a little bit hotter, or the reverse operation. Okay? So this is the other circuit which makes the decision. Let's call it N2. Okay? Temperature transfer to voltage, and this voltage you want to feed N2, which makes the decision, and that decision makes you turn the heat pumps on, for instance. Okay? Now, you cannot directly connect N1 to N2, because when you do that, this is no longer open circuit. Your design condition or design assumption breaks down, and who knows what circuit in that case will perform. But you want this voltage information to be transferred to N2. That's one thing you want. You also want that this thing remain open circuited. At least N1 should feel that its second port is open circuit. In that case, what you do is you use a buffer. Okay. So here, there's a buffer, plus, minus, and here, happens is this here is, this count is very, very tiny, so we can take it in our infinite gain op-amp model. We can take this to be 0. If this count is 0, that means N1 will still feel that this pair of terminals is open circuit. But despite that it's open circuited, this voltage here, okay, is transferred to output voltage. Therefore, N2 will get information from N1. So this voltage information is transferred to N2, but that's being done without disturbing the internal operation of N1. Okay. Here, the buffer or use of buffer prevents N2 from loading down N1. Now, let's very briefly talk about also what would have happened instead of constructing this feedback line between V out and V minus, or out terminal and minus terminal. What would have happened if we construct the feedback loop between the output terminal and the positive labeled terminal? Okay. So how about the following? This time, this feedback is called positive feedback. Now, if you figure out the input-output characteristics like we did for the negative feedback case here, because topology is very simple, you can just obtain it in 2 lines. This is the curve that you can obtain. V out, excuse me, V in, V out. You'll see that for linear region, characteristics is the same. ES minus ES, and here we have minus ES and ES. Okay. Now, if you then you compute the or they make the analysis for the positive saturation and negative saturation regions, you figure out that the condition for positive saturation is that input voltage is less than ES. Okay. So therefore, you go in that direction, and symmetrically, you go to the other direction for the negative saturation region. So, according to this curve, when, for instance, the input voltage is in between minus ES and ES, somewhere here, there are 3 possible operating points. One here, positive saturation region, one here in linear region, and one here in the negative saturation region. Okay. Now, mathematically speaking, all 3 operating points seem to be possible, but in practice, what's going to happen is you will never be able to keep the op-amp in linear region. Okay, it will either jump to positive saturation region and it will stay there. It will be a stable jump, or it will jump to negative saturation region and it will stay there. Therefore, the output voltage is either at plus ES or at minus ES and never in between. Okay, according to that, due to this, we call this operating point stable. Okay, the operating points that correspond to saturation regions are stable, whereas this guy is unstable. Therefore, this as a voltage follower, in which we want the output to follow input, at least input when the input is small enough. This as a voltage follower is a very unsuccessful design. Okay, it will not work. But it has some very important other applications, and those who are interested can find them in various books. In particular, such characteristics are used to obtain oscillator circuits. Okay, so this is, although you cannot use this as a voltage follower, but it has some other uses in some other applications. Okay, so let's put this down. That is in practice. Open. We'll quickly jump to either positive saturation or to negative saturation voltage under energy states. Okay, that's why we call these two operating points as stable and the operating point corresponding to the linear region as unstable.